So in this video, we're going to cover the second half of chapter 16, which involves calculating equilibrium constants or equilibrium concentrations when using the ICE table, among other things. So an ICE table, first to reiterate, we have the two different types of equilibrium kind of constants. We have the non-equilibrium constant, which is the reaction quotient, which is Q. And then we have the equilibrium constant, which is K. And they're both capital K. And they're both calculated the same way, which we had this reaction that is A plus B equals C plus D. It would be the products over the reactants to the exponential power of their coefficients. And we can have, just like we have for K, we can have a Q value for gases and for concentrations, meaning QC and QP. So we can do the same exact thing we did for K, but for this reaction quotient, which can be used to express the concentrations or the relationship between the products and reactant concentrations at any point in the reaction, not only equilibrium. If Q equals K, then it's at equilibrium. If Q is greater than K, that means when the reaction proceeds, it'll try to decrease, meaning the quotient will decrease until it gets to K, meaning the reaction will go in the reverse direction. So let's review that real quick. If Q is greater than K, meaning if at the point we calculate Q, the reaction is more towards the product's concentration, in order to get to K, the reverse reaction will be favored and the reaction or the products will decrease and the reactants will increase. If Q is less than K, that means Q is more heavily towards the reactants. So that means the forward reaction will be emphasized or will go faster until Q gets to K. And if they're equal, that means the reaction is at equilibrium. So there's just a summary of that. So what we want to do is we want to determine what we can do with an ICE table. So here's a couple of things. Or here's an example. So a reaction mixture initially contained at 0.25 molar CO and 0.4 molar O2. At equilibrium, the concentration of CO2 is 0.15. Calculate Kc. So here's how we do an ICE table. And we know how we need to do an ICE table is because we can't calculate Kc directly. So Kc, remember, is the equilibrium constant. To calculate this, we need the equilibrium concentrations of all of the reactants and products. We don't have that. We only have the equilibrium concentration of CO2. But to get the other ones, we can do an ICE table. So to do that, ICE stands for initial, change, and then equilibrium. So originally, the reaction mixture initially contains 0.25 molar of CO, 0.4 molar of O2, 0.4 molar. And then we don't know how much CO2, but it's assumed it's zero because we have no products to start out with. The change. What happens when the reactants become products is the reactants decrease. And they decrease by 2 times, or in this case, CO2's case, they decrease by their coefficient times a certain concentration until it reaches equilibrium. So we can represent that change by negative 2x. The change of O2, since its coefficient is 1, is just minus x. And then since the change for CO2 is a product, we do plus 2x because that is the amount it is increasing by. I know this is very brief, but in class I'll explain it in more detail. Then for equilibrium, we simply add these up. 0.25 minus 2x, 0.4 minus x, and then for equilibrium, we can say at equilibrium, the concentration of CO2 is 0.15. 0.15. We know that. So we can say from this information right here, we can solve for x because we know that 0 plus 2x equals 0.15, meaning x equals 0.075. That's very important. We could then use that to calculate Kc. How? Well, at equilibrium, we know Kc is equal to CO2 concentration squared over the CO concentration squared times O2 concentration. Now this is going to equal CO2, which is 0.15, 0.15 squared over the CO squared, which is 0.25 times 2 times X, which is 0.075, all of that squared, times the O2 concentration, which is 0.4 minus X. So 0.4 minus X, which is 0.075. So this is a lot to put in your calculator, but make sure to do it step by step, and you'll get the right answer for KC. We're not going to go through the calculations here since this is a review video, but basically that is how you do an ICE table. We will do another example right now, and we'll just set up the ICE table here, and then we'll continue. So in this case, we have 2 molar of I2 and 2 molar of Br2 initially present in a reaction mixture. So here's our reaction. We can just say that we have our ICE table, ICE. And initially for I2, we have 2.0. For Br2, we have 2.0. And for IBr, we have 0. Calculate the equilibrium concentration of I2, Br2, and IBr if Kc is equal 100 at 425, if Kc equals 100. So we know that Kc equals 100. Very important information. So what we can say again is the change of the reactants is always decreasing because the reactants that are initially present will be turned over into products. So we can say since the coefficients of these reactants are 1, we could say the change is minus X and minus X. And we could say the change for IBr is plus 2X. Then our equilibrium will be just adding up the I and the C to get the E. 2.0 minus X, 2.0 minus X, and then 2X. Kc now equals 100. So we can make Kc equal 100, which equals the products, which is, well, we'll put the general term first. It will be IBr squared over concentration of I2 times the concentration of Br2. And we can fill this in with values that are related to X in order to find X. And then we can divide this by 2.0 minus X times 2.0 minus X, which this can actually be simplified a lot into 2X over 2 minus X, whole thing squared, equals 100. Take the square root of both sides. You get 10 equals 2X minus 2.0 minus X. Then you can cross multiply to both sides. We'll do that now. We cross multiply to both sides. You get 2X equals 20 minus 10X. Add 10X to both sides. We get 12X equals 20. And then X equals 20 over 12, which I think is 1.67. So I know that went through that pretty fast, but then our answer is asking, or question is asking for calculate the equilibrium concentrations. So that's only focusing on this E column. So we can just do for the I2, it would be 2.0 minus 1.67. For the Br2, same thing, 2.0 minus 1.67. And then for IBr, it would be 2 times 1.67. And these would be your equilibrium concentrations. So then there's other examples with that. We can approximate that for if we have a large initial concentration and a small rate constant, or sorry, a small equilibrium constant, meaning the reaction is heavily favored towards the reactants, meaning it's a lot less than 1, we can say that the change, meaning X, so if we were to do an ICE table, this 2 minus X, we can assume this X would be 0 in cases that have a very large initial concentration and a very small rate constant, which means the reaction will go towards the products in a negligible amount. So if in that amount is if the X value calculated is less than 5% of the initial concentration. So then we can say, oh, it's basically not going to change. So the last thing we're going to talk about is disturbing equilibrium. And this is what we call Lachatellas Principle. So it's saying that if we change either the temperature, the volume, the reactant or product concentration of an already in equilibrium reaction, what is going to happen to the reaction? And any of these disturbances and trying to restore equilibrium is what we call Lachatellas Principle. So it guides you on what's going to happen. And there's some things that we should think about is that it's not affected by the addition or subtraction of solids and liquids, meaning non-aqueous materials. Because as we talked about before, aqueous materials are the only thing that are going to be in solution and that we can calculate concentrations for. If you have solids or pure liquids, they are going to be present and may take part in reactions, but they're not going to be part of our equilibrium constants or reaction concentrations because they're not part of a solution. So the first thing we're going to talk about is adding reactant. If we add a reactant, and we'll just go very basic. So we'll just go brief. If we add a reactant, the reaction goes towards the right. Think of it as a balance. If you add too much to the left, in order to make that balance level off again, that reaction has to go to the right to balance it off. That's exactly what happens. So you add reactant, it proceeds to the right until equilibrium is restored. And keep in mind, the new equilibrium position is there. But the concentrations of reactants and products will be different because there's more stuff. But the value of the equilibrium constant will stay the same. In all of these changes, it does not change the equilibrium constant. Keep that in mind. Doesn't change equilibrium constant. It just changes the concentrations that are at equilibrium of the reactants or the products. So now if we remove a reactant, what's going to happen? The reaction proceeds to the left until equilibrium is restored. So same concept, meaning if you add too much to the right of the scale, to balance it off, has to go to the left. And then you can read all that. You can pause the video and read these points, which will be talked about in lecture. The effect of concentration changes on equilibrium. So it's just the basic, what we just talked about. Equilibrium shifts away from the side with the added chemicals or towards the side with the removed. So it's to restore an equilibrium. Getting back to baseline is what we're trying to do. And there's just a graphical idea. So then changing the volume. Now, changing the volume, would that apply for all types of reactions or just gases? And the answer is just gases, because for aqueous equilibrium, doesn't matter if it's in a small beaker, large beaker, you're adding solutions with concentrations. For gases, the pressure is a large component of how things react. Things can react at a higher pressure as opposed to a lower pressure. And the pressure dictates how much the molecules move. So it makes sense that if you change the volume of a gaseous reaction, it changes the pressure of the reactants and products, and in which the pressure equilibrium has to be restored. So first is we'll talk about reducing the volume. And think about it this way. Ideal gases have reactants and products. The moles of the reactants total, meaning the addition of the coefficients, might be larger or smaller. There might be a change in moles going from reactants to products. If there is, that means as the reaction proceeds, let's say towards the products, the pressure changes. It can go higher or it can go lower. So here's what we can say. If we reduce the volume, this means we're increasing the amount of space that the molecules can move, decrease it, and we're increasing the pressure. If we increase the pressure, in order to relieve that pressure increase, the equilibrium will shift, or the reaction will shift towards the side of the reaction with fewer gas moles or fewer gas molecules. So in order to restore this kind of even pressure to where the partial pressures of the reactants and products will keep the equilibrium constant exactly the same, we'll keep it constant. So decreasing the volume causes the reaction to shift in the direction with the fewer gas moles. If we do the opposite, increase the volume, this is going to decrease the pressure. If we decrease the pressure, in order to increase the pressure enough to get to that same pressure that equilibrium was restored at, or to restore equilibrium, the reaction will shift in the direction that has the larger number of gas moles. So think about it as an ideal gas situation. Decreasing the volume makes everything have a higher pressure. We want to relieve that pressure. So the reaction is going to go where you have less gas moles. If we increase the pressure, where we increase the volume, we're going to decrease the pressure. To increase that pressure back to its equilibrium constant pressure, ratio of pressures, we want to move the reaction in the direction of the greater number of gas moles. And this doesn't change if you have inert gases or different types of non-solution entities in it. So let's talk about reactions now that are exo or endothermic. Now for exothermic reactions, or for either of these, for Lachatellas Principle, where we're talking about the effect of temperature, we can consider endo and exothermic reactions as just like normal reactions, but you have heat as a reactant or product. So for something that's exothermic, meaning the heat is released, we can put heat on the right side of the equation. Now, if you want to increase temperature, that's like you're adding heat. So if you add heat, meaning this is just like the same as a normal product or reactant, if you add heat, the reaction will go towards the left, away from the heat, because this is an exothermic reaction. So we want to balance it out. For this case, if you have an exothermic reaction, if you remove heat, the reaction goes towards the heat to restore that kind of equilibrium. And adding heat will decrease the value of K. So K is based, so in this case, K changes because it's based on a certain temperature. So K is only true at a certain temperature, as we've seen from the rate constant. So rate constant changes with temperature. And so does the equilibrium constant based on, rate constant because of Arrhenius equation. If we have an endothermic reaction, this means heat is on the left side. If heat's on the left side and we add heat, the reaction will go towards the right. So it's kind of like we're balancing out this teeter-totter, same exact approach. And adding heat to an endothermic reaction will increase the value of K because it goes more towards the products. And that would increase the ratio. So that's basically it. Here are some ice table practice problems you can do. You can pause and do some work on the screen, but we'll go over these in lecture. So I hope you learned something from this video, and stay tuned for more information during lecture and the full video.